For invasive brain surgery, it's important to define both the areas in the brain that are bad, so to speak, the areas in the brain that produce epileptic seizures, for example, but also the areas that are responsible for producing important human functions such as speaking or moving. And when one knows about both of these areas, surgeons can then plan which part of the brain to resect without affecting these important functions. Up to the present, there have been several different technologies that are used for identifying important areas in the brain. They're also called eloquent areas. The most notable of these technologies are functional magnetic resonance imaging, or fMRI, and electrical stimulation of the brain. Electrical stimulation of the brain has been used for several decades, at least five decades, in many large clinics worldwide. And the basic principle is pretty simple. There are electrodes, and clinicians apply current between these electrodes. And when that kind of electrical stimulation produces function, for example, it makes the hand move, or disrupts function. So, for example, it stops a person from speaking. A person is trying to speak but can't speak anymore. Then the clinician can then learn that this particular area in the brain is responsible for this particular function. Now, the difficulty is that all these current technologies, including electrical stimulation, even though they've been used for many decades, they have a lot of problems. Electrical stimulation in particular takes a long time. It may take 5 hours on average. It can also produce epileptic seizures. So in people that have epilepsy, for example, they have a brain that's essentially on the hair trigger to producing epileptic seizures. So when one then provokes that brain, that diseased brain, with an electrical stimulus, there's a reasonable chance that this may lead to an epileptic seizure. And that, of course, is not only inconvenient and can be harmful and so forth. Of course, the person then is not able to comply anymore, and the mapping, this functional mapping, can perhaps not be completed before the surgery. So this creates a lot of difficulties in the clinical environment. So over the past 10 years or so, we've been developing a completely new way of mapping function in the brain. And that new way does not depend on electrically stimulating the brain. Instead, we use the same electrodes that are already implanted in these individuals for the electrical stimulation mapping, but we don't stimulate. We actually simply record brain signals from those areas. And we essentially watch what happens when the person moves a hand, for example, or speaks. And we look for particular patterns in those signals that we are recording from those electrodes, and see how they change and when they change. And those areas that change in their brain activity when the person is producing that function, those are the areas that are responsible for this particular function. So with this, all a patient has to do is execute simple tasks. They just speak, just like I speak now. That's all they have to do while we record signals from the brain and analyze those signals with sophisticated signal processing and statistical techniques. So this technique, not only does it not require electrical stimulation of the brain, it is also very rapid. It may take 5 minutes. So just as I'm speaking right now and as I'm moving, a clinician would see a map of that person's brain emerge on the computer screen, and there will be a location that's responsible for hand movement. There will be another location that's responsible for speaking. There's another location perhaps for moving the tongue and things like this. And that all happens within just minutes and without actually having to stimulate the brain. So the advantages of this new procedure are that the technique is very rapid. It just takes a few minutes instead of a few hours. It's very easy to use. It doesn't require complicated equipment. It doesn't require a scanner that costs a lot of money and procedures that can only be used by highly trained experts. It can be used by people that have very little training. So it's very easy to use. And it doesn't increase the risk of a patient having a seizure. So with this technique, then it's much more likely that one can produce a full map of the different functions in the brain instead of maybe only a partial map because it takes a long time or because there were seizures involved and things like this. So it's not only more comfortable for the patient, it's also better for the clinician because they can get the results they need and very quickly and very reliably. So we've been developing this technique for over 10 years now, and we started with very basic research in trying to understand how brain signals change when we engage in different tasks like moving and things like this. We then took that understanding and implemented a computer algorithm that would take advantage of that understanding. And then started to use this computer algorithm and the resulting software together with clinicians in trying to understand how that could be useful in a clinical environment and with actual patients. So several years ago, we've developed a prototype that was completely functional and that we've then validated in initial studies with actual patients, with clinicians in several different clinics. And we then licensed this software prototype to a company called G-Tech. And that company, G-Tech, then took this initial prototype and developed it further into an actual clinical product that's called CordIQ. And this product is now sold worldwide and has achieved initial adoption, and G-Tech is now close to receiving regulatory approval for this product, and we expect that this will greatly accelerate the even further adoption. In the future, I fully expect that this completely new functional imaging technique will, at the very least, greatly complement existing methods such as electrical stimulation. And I wouldn't be surprised if eventually wouldn't actually completely replace electrical stimulation.